let's talk a minute about how much energy is stored in the magnetic field in an inductor. An inductor works in a circuit with magnetic fields much the same way that a capacitor works in a circuit with electric fields. Both inductors and capacitors store energy. You can retrieve energy from a capacitor, you can retrieve energy from an inductor, and they're very much a part of alternating current circuits. So I've got here an inductor. We'll just assume it's a coil, it's a long coil, just to make the calculations easy. So the magnetic field is equal to mu times N over L times the current through it. When I put a current through that coil, that induces an EMF across the coil. And I could ask, how much energy am I storing in the magnetic field in that coil? Let's see, the voltage that we measure across the coil is going to be equal to minus L di dt, where L is the self-inductance. We calculated that before. And we know that power, which is equal to energy for time, is just going to be equal to the voltage times the current. We use that with, you can use that with any part of a circuit, whether it's a resistor or a capacitor. Okay, so I'm going to take this and add it to this, so I get power is equal to du dt, that's energy per time, that's equal to VI. And if V is equal to minus L di dt, so that's equal to minus L times di dt times I. Okay, if I then commit a math sin, I'm going to cancel out the dt's, and I get that du, the amount of energy that's added to that magnetic field in the coil, is equal to minus L I di. So as the current increases, so does the energy increase. So if I want to find out the total energy enclosed in the coil, I need to integrate from zero current to whatever the maximum current is. So I could do U total. The total amount of energy stored in the coil is equal to the integral of du. That's equal to minus L times the integral of I di, from I is equal to 0 to whatever the final I is, the final current is. And that just gives us I squared over 2. So that's equal to minus 1/2 L I squared, I final squared. I wouldn't worry about the minus sign, it's not important in this, so I'm going to just remove it because I don't like it. And so that gives us the amount of energy that's needed to charge up a coil to a certain current I. And so by producing that, we actually produce a magnetic field, and we're storing energy in that field just like we did with a capacitor. All right, so what does this have to do with the energy in the field? Well, what we're going to do now is we're going to calculate the amount of volume of field in the field that we have and see how much energy is stored per unit volume of field. So I'm going to erase this. So the energy stored in the inductor is equal to 1/2 L times I squared. Okay, let's see, that's 1/2. L is equal to the self-inductance of the coil is equal to mu0 times the number of turns squared times the area of the coil divided by the length. Okay. And if the B field is equal to mu 0 n over L times I, then we can solve this for I in terms of the B field. And so our I squared then becomes B times the length over mu 0 n squared. So I put in the expression for the self-inductance, I put in the, for I put in an expression that relates to the B field, and you can see that a lot of things are going to cancel out, and I'm going to end up with, let's see, this will be canceled out. Well, let's just go ahead and do it the whole way. 1/2 mu 0 n squared A over L times B squared L squared over mu 0 squared n squared. So the n's are going to cancel out. That was a mu squared. That's going to cancel out that. Still have a b squared. That's going to cancel out that. And I should get 1/2 b squared over mu 0 times A times L. All right, A times L is just the volume of the coil, right? The cross-section area times the length, so this is the volume. And so I can calculate an energy density, U total over the volume is equal to 1/2 B squared over mu 0. And that turns out to be a general result. Anytime you have a magnetic field, the energy density is 1/2 B squared over mu 0. That's the number of joules per unit volume. Remember, we had something similar with electric fields. For an electric field, U total over volume was equal to 1/2 epsilon 0 E squared. This mu 0 and the epsilon 0 keep popping up, and we're going to unify those together later on. Okay? So these are two very important quantities that we'll use later on.